So we've introduced this idea that impulse is a sort of way to do before and after modeling to sort of add up what the total influence of force is over some period of time when you don't know so much about what the details of the force are. Let's walk through an example of that and that tries to get at what the utility of impulse is. So this video, my intention is to try to get at the utility of impulse and to do so mostly by walking through a couple of physical examples. Before I walk through the physical examples, let me just highlight what the key points are from a utility perspective. One key point is that actually it's often the case that it's really hard to model force and a lot easier to talk about what impulse is. So often force details are hard. And they're particularly hard when you're talking about sort of very short time scale kinds of interactions. Forces can change by large orders of magnitude. It can be really difficult to talk about what the force is. The second thing is that often impulse can give you insight into what's going on with the forces, even though the actual force details are hard. So it's often possible to go from impulse to sort of physical insight without having to think too hard about what the details of the forces are. And then finally, of course, impulse has simple utility in that sometimes it's just easier for calculational purposes. And anyone who did a project on pool breaks in ModSim knows that it's a whole lot easier to deal with the pool break by thinking about momentum conservation, that is, thinking about impulse, than it is by thinking about what the details of the forces between pool balls are as they collide. Okay, so let's do an example of using impulse, and the example I'm going to do is just a sort of simple example that has to do with a ball that's bouncing on the table, right? So there's a ball bouncing on the table, and what we're interested in is trying to understand, how hard does a ball actually bounce on the table? In other words, what's the sort of what's the strongest force that you actually would, like if you were to put your hand under that ball, is it going to break your fingers or is it going to be relatively painless? How hard do balls actually hit when they hit the table? And how does that depend on what the sort of makeup of the ball is? Like, why is it that, bouncing a tennis ball off your hand hurts a lot less than, say, bouncing a super ball off your hand? If that is the case? So let's think about that. And to think about that, I'll recall that first of all, this sort of idea of impulse is that impulse is what the change in the momentum is. And so in order to figure out the change in momentum, let's just assume that the ball is moving down at some velocity minus mv j hat initially, and it bounces, and we'll assume it's just a perfect bounce. So it starts bouncing, it comes back off the floor at plus mv j hat. Okay? So if we ask the question, what's the impulse here? The impulse would be, actually, sorry, that's what its momentum is when it's going up, its momentum when it's going down. The change in momentum then is going to be the final momentum minus the initial momentum. The final momentum is plus mv j hat. The initial momentum is minus mv j hat. And so the impulse here is simply 2 mv j hat. Okay? So we can easily say what the impulse is that the floor has exerted on the ball. Okay? Notice it would be a whole lot harder to say what the force is that the ball has exerted, because that force is going to depend on what the structure of this ball is, what kind of material it's made out of, how long it's in contact with. And there's a lot of stuff in the force, whereas it's almost trivial to say what the impulse is, and in fact it's also handy for modeling. Like you might, for example, introduce the idea of a coefficient of restitution that tells you what the sort of ratio of these momenta are as the ball bounces. Okay, so now that we know what the impulse is, can we use this impulse to gain physical insight? Because one of the ideas here is that you can actually use impulse to say something about what the forces are. Well, let's think about what must be happening when the ball hits the floor. Well, when the ball hits the floor, it first touches the floor, it then begins to deform, right? It deforms some amount. Maybe it's a really bouncy ball, so it deforms like that, and finally stretches back out and then leaves the ground, right? So it looks something like that from a keyframes perspective. So if I think about where the center of mass of the ball is, right, the center of mass is at its lowest point here, and then it's moving back up into the air. Now, if that's what my picture is, I could also think qualitatively about what the force is that the ball is exerting on the ground and what the force is that the ground is exerting on the ball. So if I actually tried to plot the force of the ground on the ball as a function of time, right? Well, pretty clearly at this instant, it's going to be at its highest, right? This is when the ball is the most compressed, and so it's going to be pushing down against the floor the most. The floor is pushing back up against the ball the most. There'll be some force here, some force here. So maybe the force of the ball on the ground or the ground on the ball, maybe it looks something like that, right? We don't know exactly what it looks like, and that's part of why impulse is handy, is that even though we don't know exactly what this shape is, we do know what the integral of this is, right? When we integrate this entire thing, this integral tells us what the change of momentum is, right? The integral of this force is the impulse. On the other hand, we can start to think about like how big this is if we just make some simple approximations. So one approximation we might think is to say, well, let's ask the question, how long is the ball in contact with the ground? Well, you could make a reasonable estimate of that by saying, well, if the ball compresses a certain amount, so let's say the ball compresses by some distance, decompress, right? Maybe that for a really bouncy ball, maybe that's a one ball radius, so the ball actually compresses from being round to being sort of half of round. Maybe if it's a really hard ball, the decompress would be 1/10 of a radius or 1/100th of a radius. But if we assume that the ball compresses some distance, then if you look at the picture, it seems like that time of contact times whatever the initial velocity of the ball is should be on the order of that compression distance. In other words, the time scale of contact is on the order of decompression divided by what the incoming velocity of the ball is. Okay? So we don't know what the force is exactly, but we can say, this time scale is around decompress divided by v. So if we think about, say, a soft rubber ball, so let's say a soft rubber ball that's about, yay big, maybe decompress is 1 centimeter, right? So for a rubber ball, decompress is 1 centimeter, velocity is maybe 10 meters per second. So the time scale is going to be 10 to the minus 2 decompress meters over 10 meters per second. So that rubber ball is in contact with the ground for on the order of 10 to the minus 3 seconds. Okay. But now that we know what the time scale is, we could estimate about how high this force is, right? I mean, one estimate would just be to say that time scale times that force is going to give me about what the change of momentum is. I can also say, well, if I look at this really, maybe half of that time scale times the force will give me what the impulse is. But in any case, I can certainly make a guess of that, right? So let's say it's 1/2. So 1/2 of the time of compression times the maximum force, right? That's my estimate for what this impulse is, right? Has to be equal to what the change of momentum is, which is 2 times the mass times what the speed of the ball is when it's coming in. And I've been a little bit sloppy with turning things from vectors into scalars here. Really, F max should be in the j hat direction, and this should be 2mv j hat, and this should be a vector. Okay? And notice that at this point, I can start to say something about what F max is. The maximum force is going to be about 4 times the mass of the ball times the incoming velocity of the ball divided by the compression time, which I could also write as 4 times the mass times the velocity of the ball times the velocity of the ball again divided by the compression distance. Now, from an insight perspective, what does this actually tell us? One of the things it tells us is that if you are dropping something on the ground that doesn't compress very much, like a brick or like a ball bearing, decompression is going to be really small, and this maximum force is going to be really large, right? The other thing you can start to see is that as the speed that something is hitting goes up, the actual force that is required to make it bounce goes up as the square of that. So dropping it at twice the speed is actually going to result in 4 times the force. And this sort of gives you some insight into why, for example, it's a lot more painful to have someone drop a brick on your hand than it is to have someone drop a basketball on your hand. Even though a basketball and a brick they're not all that different from a mass perspective, so the mass is about the same. But with a basketball, decompression might be on the order of 1 centimeter to 5 centimeters. And with a brick, decompression is probably on the order of 1/10 of a millimeter or 1/100th of a millimeter. And so the forces that you're going to experience when that person drops a brick on your hand are very, very different from the forces you will experience when someone drops a basketball on your hand.